USB proxy.
Oh, OK. That was, it's all right. I need to light up my keyboard now. All right. No. All right. Oh, yeah, something like that. Excellent, disco style. Hi, my name's Dominic Spill, and I've been working on a project called USBProxy, and I'm going to talk about trying to block writes to USB mass storage devices using it. And it's a little project I've been working on for a while, and I just used the application this time to, I decided to apply it to mass storage devices rather than anything else. But I'll try and give a quick demo of some other stuff too. So I'm all aware you can see me. I've only got a picture of myself on the slides because someone's going to read these later and not recognize me, and I like my own face. I work for Great Scott Gadgets. I write open source software, mostly working on Ubertooth and Daisho and things like that. I work on a few things in my own sort of spare time. This is one of them. FCC.io is a redirector to do FCC filing lookups because it's super annoying trying to find the search function on their page, and that's totally worth looking at. And I've had a little play with some hardware. There's BeagleDancer, which I'll show you in a minute, and there's PS2Tap, which has never really worked and is sort of pointless anyway. But you got to start somewhere, right? So the other person who isn't here is Adam Stasiak, and he's done a lot of work on USBProxy as well. He wanted to use it to, his main goal was when playing Xbox with a friend, he wanted to inject button combinations without having to actually do them on the controller. And it's one of those things that he thought one afternoon, oh, this might be fun to try, and I'll get a FaceDancer, and it's an excuse to play with it. And it got somewhat out of hand, and we've been working on it for about 8 months. And it's this huge kind of system that we've built around it. But he's got a blog, which is Controlling Xbox, where he talks about injecting button presses and things like that. And he's done a lot of the work on the core library of USBProxy with me. I don't have a picture of him. I have no idea what he looks like. I met him on the internet. So if he's here, hi. So I mean, I'm going to go ahead and assume that I don't even need to ask the question, does everybody know what USB is? If you don't, then there might be slightly high barriers to entry for this talk. But it's like the device interface that you get on every home PC, every laptop. Most tablets, most Android tablets at least, have a USB port of some sort. It's still the communication method used for updating your iPhone or whatever. It's like the interface that replaced serial and all these other kind of different methods that we had back in the late 90s. And it's so popular, so ubiquitous. I mean, yeah, the 2 billion devices a year is the last figure I could find. That was 2008. And I swear that it must sell that many memory sticks a year now. So it comes in a variety of speeds. I'm only dealing with low, full, and high speed at the moment, which is up to 480 megabit. You'd know it as USB 2. The super speed stuff we're looking into, but can't be done with this solution. So my point of view for looking at this, I wanted to build a tool that people could use for security assessments. I wanted people to be able to look at the drivers and fuzz the drivers, and I want them to be able to look at device firmware, and obviously there's a talk at Black Hat tomorrow or Thursday about looking at USB device firmware. And I wanted to just be able to have a look at the packets going across the connection. I literally want to be able to do the same things everyone else does with Wireshark for networking stuff. I want to be able to do for USB. And we build USB devices as part of our work at Great Scott Gadgets, and it's nice to be able to work out what's going wrong across that connection. And there are lots of commercially available devices that do that, but we thought we'd quite like to build something open source and much cheaper. So you can build a device that will let you inspect the packets in the middle of a USB connection, and you can get some, and they range in price from a couple of $100 to a couple of $1,000. They're really good. The commercial ones, the like $6,000 one is excellent, but it's also $6,000, and I can do a lot more with the change if I build one for $40. So I decided to go for this. And most of my history is building Bluetooth sniffers and Ethernet taps and things like that. So it's pretty much the same style of work, but on a different bus. So I Can I have a quick show of hands? Who's familiar with the FaceDancer board? Anybody seen it? Travis Goodspeed designed it. It's basically a good FET because he has way too many MSP430 chips hanging around, and then he put a USB device chip on the front end. And the idea being that you use it to prototype a device in Python on a host and act like that device. And he'll give you a blank PCB for free, and you can just go and build the board yourself. Or you can buy one. I think they're about $70. They may be a bit cheaper than that now. I can't remember. But you can go and pick up one of those. And most of this comes from his work with Sergey, where Sergey said, well, USB is basically a network. It's exactly the same. Like, why do we not have the same tools for USB that we have for Ethernet? Like, we have so many tools to explore. You've got two hosts that are communicating via Ethernet, and you've got so many tools to look at that connection and explore the data going across that. Why are those tools not available for USB? And why are we not able to inject traffic and sniff traffic and do all the things we want to do to that? So that's where FaceDancer came from. And they look like this. So try and give a quick explanation. This is an FTDI to serial chip, an MSP430 chip, and then a Maxim integrated USB device chip. And the idea is it speaks serial, so you don't need firmware and things like that initially, and you don't need much host code or drivers or anything, because it just speaks like standard serial, uses the MSP430 to do the translation, and then speaks SPI to the chip. It speaks SPI at 1 megabit, which is incredibly slow for a lot of the USB applications you want to play with. There's a huge latency because you've got to go from that device, every time there's a request from the host, you've got to go back to the other host over that 1 megabit connection. We store the connection. You do some stuff in Python. You send your data back. We uninstall the connection and send it, and then we wait for the next one. And so it's incredibly slow. And this isn't mine, but mine looked even worse than this. I actually managed to lift some of the tracks off the board with my terrible soldering technique. This probably explains why I don't really do hardware. So it's kind of difficult. And some people decided to build one that attached to the Raspberry Pi, and a guy called Philippe in France. And the idea being that you can run the SPI interface on that at 26 megabits. So that's pretty useful. You can kind of now work at least 26 megahertz for your USB connection. You're getting up there. You can start dealing with proper devices and act like a real device. And Travis just put out a tweet saying, would anyone mind designing one to the BeagleBone? So I did. And it's largely due to other people's work that it works. But that's the design, and it looks like that. And then this is the only working one attached to my BeagleBone. And it's basically exactly the same thing. It's exactly the same piece of kit as FaceDancer, but you take off that expensive front end with the FTDI serial stuff and the MSP430, and you just plug the SPI section straight in. And then I went to my boss, and I said, hey, Mike, I built this thing. Look at me, I did hardware. His immediate response was, yeah, but you can just do it in software. Why did you do the whole spend a weekend designing a board, wait 3 weeks for it to be manufactured, be terrible at soldering it thing, when you could have written some code? Which I hadn't realized. And it turns out that the BeagleBone Black has USB on the go built in. And I knew this. Like, you get a BeagleBone Black, it comes with a firmware on it that acts as a mass storage device. It acts as a USB serial device. So why can't we just make it act as any other device we want? So we wrote USBProxy. And USBProxy is a C++ firmware that allows you to move traffic from the host port on the BeagleBone Black to the device port and vice versa. So we don't have to bother with anything. It's relatively high level. We don't have to bother with sort of packet checksums and things like that at the kind of low level. We just get messages passed across at the libUSB level. Like kind of, if you've ever written any code that interacts with USB devices, libUSB just kind of gives you this high-level thing. You go, here's a block of bytes. Send that to the device. Or go and fetch me some bytes from the device. And that's pretty much how it works. There are a few extra little bits and pieces in there, but largely it's fairly high level. And we built it on the BeagleBone Black because it's open source hardware, which is something we believe in. It's incredibly cheap, and it has the capability. So one question I get asked sometimes is, oh, does this work on the Raspberry Pi? The Raspberry Pi doesn't have a USB device port. So the Model A kind of does, but I've never been able to get it to work on there. But the BeagleBone is sort of the cheapest possible board that you can go out there and buy and just run this code on there. And so it's kind of our target platform. The only problem is they're really difficult to get hold of. So I am currently targeting a couple of other boards. The OLMX Lime is based on a little Allwinner A10 chip. And that's about the same price, about $40, and exactly the same sort of setup. And that's quite nice. I haven't got it working on that yet, but there's no reason I wouldn't. The paralleller boards from Adaptiva, there was a Kickstarter where they built these boards that have these massively parallel chips on them, but it's just got an ARM MCU and it runs Linux, and so may as well give that a go. That's another one. And pretty much any embedded board that will run Linux with a USB device port. So if you've got a board that already runs Linux and has an embedded device port, this code will probably work on that, but I'd make no guarantees. And I'd love to hear from people who are sort of interested in that and want to give it a go. I should also skip back a couple of slides and clarify. Down here, we say built upon GadgetFS. GadgetFS is built into the kernel, the Linux kernel. It allows you to present a set of USB device endpoints as a file system. So you don't have to worry about interacting with some obscure driver. From your code, you literally read and write to and from files when you're transferring bytes to the devices. And again, it operates at roughly the same level as libUSB, so we just kind of give it a bunch of bytes and say, send this to the host. Or the host sends a request, and we just read from the file and get the request. So it's pretty simple to use, and that makes our code a lot easier and a lot more stable. So I'm going to try and give a quick demo. How am I doing for time? Have I got time to do another demo? A quick demo? Beforehand? There are more coming later. I just want to... Excellent. All right. So what I'm going to attempt to do now is to... Great. OK, so I have a keyboard plugged in. And if anyone's seen my ShmooCon talk, you will have seen this demo before. It's my sort of standard demo for this. But I will type something, and hopefully it will work. And I'm pretty sure everyone can read that and knows exactly what it says, because it's super obvious. So what I can show you I was actually doing is this. Where is my mouse? Sorry, I've lost my cursor. There we go. What I was writing was BSidesLV, because that's where we are. And you'll notice on this screen, which is where I'm SSH'd into the BeagleBone Black, I get BSidesLV written, because I'm keylogging it, which is what I was hoping to do. But on this screen, I get OFVQ FYI, which, for anyone who does the maths in their head quickly enough, will know is ROT13 for BSidesLV. So what I've done in the middle there is I've enabled a keylogger. I don't know if it lists the ones. So I've got a keylogger running, and it's dumping to standard out. And I've also got a ROT13 packet filter in there. And so the ROT13 packet filter obviously only works on HID keyboard stuff. If I were to plug any other device in right now, it would just go a bit haywire. And I didn't bother writing any error checking in there and making sure it's a proper human interface device packet or anything like that. But it's just a simple proof of concept to show that I am typing on a keyboard. The keyboard is hooked up to a BeagleBone Black, which is here, which is then hooked into my host laptop. And in the middle, I'm able to man in the middle of the connection. I'm able to change the packets on the fly and pass them over to the host. So there we go. So we've pretty much achieved man in the middle. We know we can do that. So now let's look at some applications for that. Before I do that, I should explain what the structure is, apparently. So all we're doing is we're moving packets backwards and forwards, and then we added some hooks in that allow you to put in filters to modify the packets on the fly, to filter out packets, so you can block packets and things like that. We have injectors which can inject traffic. We set up either endpoint, the host side and device side, as these proxy plugins. And one of the reasons for that is because we don't always want to talk to a device or a host. We might want to, for example, set up a TCP proxy. And the idea being that we take the USB traffic, we then encapsulate it, push it over a network, and then at the other end we have another BeagleBone Black attached to our target system, and we can then convert it from the TCP back into to talk to the host. So you can do things like do remote USB devices. And we're pretty interested in looking at that to play around with those software protection dongles. The idea being is I have a server somewhere with a couple of them plugged in and USBProxy running, and anyone who wants to use it just kind of connects, and I just timeshare the access to those software protection dongles. And we're pretty sure that would work, but no one was willing to sell me samples that I've found so far. So if anyone has any lying around and wants to give me a USB software protection dongle, I would love to hear that. So it looks a bit like this, and the project is the center section. The relayer in the middle that pushes things around is a library. It's called libUSBProxy that we wrote. And then the injectors, the filters, and the device and host proxies are plugins. So you just have a standard interface that you have to produce, and you can connect to those. So for a filter, the interface is as simple as you write a function that takes our packet struct as an argument, and that's it. All you do is you modify it. If you set a flag on the packet struct that says drop this packet, we drop the packet. If you want to modify the data in it, you can modify the data. You can do whatever you like. The injector, you just have to have a pollable like pipe file descriptor of some sort to inject, and you just like throw data down that in a given sort of format, and it produces USB packets for you, and it injects them onto the given endpoint that you've discussed and things like that. And there are some slight intricacies that you need to know about the way USB works, but I'm going to leave them out of this talk because they're not super relevant to everyone in this room. If you get into it, you can always email me, and I'll happily give you a crash course in how USBProxy and USB works. On that note, there is a talk on Friday at DEF CON called something about USB for all, which is by two guys. One's called Jesse, and I can't remember the other guy's name, but it's going to be a good crash course intro to USB if you're interested in looking at USB security or just playing around with USB devices or writing your own in software and things like that. So let's move on to what we want to look at here, which is USB mass storage. So everyone's seen a USB mass storage device. Mine's around here somewhere. No one is going to be able to see mine from where you are, but mine's a little man that I found. So thank you very much to Fox, actually, who gave it to me. But it's a little man. It's a little USB mass storage device, and all it implements is a protocol called bulk-only mass storage. And what that means is USB has these endpoints that are directional. They only go either towards the device or back. So you have one in each direction, and that's all it uses for the mass storage. So all the control messages go over there, and all the data go over the same one. So if you're sending data to the device, it goes over the one to the device. If you're reading data, it comes back over the same thing. It's pretty straightforward protocol, and all it does is implement SCSI over that. So it just uses those bulk endpoints and sends standard, really old SCSI commands. And those happen in a three-stage process. All SCSI happens in this three-stage process. You send a command telling it what you want to do with the data. You then send as much data as you promised in that command. And at the end, the device sends back a status message to say, yes, it worked, no, it didn't, whatever happened. And now this leads us to a tricky situation with our USB device, because I want to build a write blocker. So ideally, what I do is I take the write commands, and I just get rid of them. I just drop those packets. And so, let me just go through in case this was. A read command is from the device to the host. I'd like to read this block. The device sends the block back, and then it sends an OK message. The write is obviously the opposite direction. Everything is controlled by the host, obviously. The host says, I want to write to this location, this is the size. Then it sends all the data to write, and then the device sends back a status message. So I could reasonably drop all the messages in the middle and have the host think that the write had happened, but it would never get the status OK message. An alternative is I could do things like change the write to a read and read the block, and then drop both the read and the write, and the status message would still come through OK. But that turns out to completely confuse everybody because the messages are tagged with an ID. And so you'd have to copy the ID, and it gets a little bit confusing between the read and the write. First off, I could stall the connection. I could read a block from the device, And then I could just substitute the data when the write comes through and write exactly the same data through. Or I can just change the length field to 0 length and just try and write 0 length data and then just ditch the packets in between. It turns out writing 0 length data actually crashes the connection. And I have yet to discover if it interferes with Linux's kernel driver, or whether for talking to USB mass storage, or whether it interfered with the controller on the USB mass storage device. So I decided to kind of combine some of these into a single method and kind of mix and match. So instead of what I tried to do at first, and the main one is blocking the entire transaction, and that is I drop that write command, I drop the data, I do nothing with it, but then I have to somehow tell the host, OK, this is all right, everything was written perfectly fine, and my device won't produce that message for me. But luckily, because we also have injectors as well as filters, I can just inject that message. So I will attempt this right now. So hopefully, there we go. So you can see all the reads happening. This is as my host system tries to read out all these different blocks. And we can open this up and see that I have an empty USB stick here, and then again I can do B-sides. I'm terrible at typing when people are looking. And I can write a file called B-sides, and we wrote, and it was tagged, and it said, I want to write one block to this. And then I've dropped both those, and I just inject a false OK status, and we get a success message coming through. And so we still see this file here, and we can still look at it, and it looks like it's on the drive. And that's due to two things. One is that it's we've been told the thing happened OK, the connection, the write happened. The other thing is it's still in the host's file system cache. And we can flush the writes, and it'll go through. And the other thing I can do is I can open it up in LeafPan. I can type a bunch of junk in it and save it. And I can still open up, and it's still there. So the host has no idea that this write has not happened. And I'm super hopeful that the demo worked, because if the write did happen, then I'd be in trouble. But if I kill that, and I unplug the device and plug it into my host directly, very quickly see that it's completely blank, and we managed to block the write. So that's kind of useful. That's achieving what I've set out to achieve, right? I've blocked the writes, and this is sort of useful for a lot of people who don't trust a host system, right? You don't trust the host system you're connected to. You want to read some data from this. Reads happen perfectly fine, but writes will get blocked. So that's kind of useful when you're plugging in someone else's USB stick, because, yeah, reasonably they could have something on there that owned your box. They could also reasonably have something that owned the BeagleBone, but it's unlikely, and it's less likely that they're going to have a malware on there for ARM. So I'm less concerned. But it might be quite nice also at the same time to examine those writes. So does everyone remember earlier in the year there was some stuff people were talking about called bad BIOS? And the idea there were various ways it was propagating. One was with sort of ultrasonic communication. And another was whenever I plug in a USB stick, it copies itself to the USB stick and it infects certain things. Well, it would be nice to see what's being written to the USB stick, because when you plug it in, you think the only thing, or you may think that the only thing that's being written is what you're intending to write, what your system is intending to write. But obviously, that's not always the case. So it might be nice to have a look at what's going on that connection. All right. So again, it's come up as a device. And again, I'm going to create a file called B-sides. And, oh, this font is way too big. But what I've done, so if the fonts are normal size, this looks like a really nice diff and hex dump. And I had not considered that I needed it to be this huge. But what you'll find is it's colored in red, the old blocks, and in the old bytes, and in blue, the new ones. And this is the change. So the left-hand side, should be left-hand side, is the original data. that was on the device, and it cached the read at some point when the device read from the when the host read from the device. But as we've come to give a write, it's gone, looked in the cache, said, yeah, this block's in the cache. Why don't I compare what's going between the two? And so what we can see here is, I should clarify, this is a FAT16 file system. So the file name is up there. It is also right here in uppercase characters. And that's part of just the way FAT16 works, because it's a horrendous old file system. An interesting question is why I'm using FAT16. I'm using FAT16 because I only found out this week that the reason that some of my code, so some of my USB sticks, sorry, don't work with my code, is that my code only seems to work with FAT16 at the moment. And I have absolutely no idea why, because I'm not interacting with it at a file system level. I'm interacting with it up at like the USB protocol level. But anything with a more modern file system on the device does not work. I'm pretty sure it's a very small bug to do with the way that the device decides which method of USB storage protocol to use. And I can just force it to use bulk only. But for some reason, it defaults to this for FAT16, so that's what we're playing with today. So we can look at the diff of the write, and we can see what's being written, and we can say, well, that looks like the thing I expected to be written, so I'm happy with that. Or at other times, if you suspect you have this bad BAS malware or whatever, you can say, actually, it looks like something else is being written that I didn't intend to write. And then we can start to examine that and look at how that is affecting our system. So let me eject this device. I should say this is very experimental code. Another thing that always has to happen is between each usage, I have to unplug and reinsert the device. And again, no idea why. So what I've done is I've just shown that we're able to block writes. And so if you're connecting to your memory stick to a sketchy-looking host, you can just put this thing in the middle, and it will stop anything being written, but you can still read your stuff off it, which is kind of handy. And I've also shown that we can start to examine those writes and how they're happening, and what data is being written using that diff and caching the blocks in the middle. There are actually some oddities to do with this block caching. Almost everything I've used, the file system reads the blocks first, and then writes over the top of them. So the block is always in the cache. And this morning, I just tried this out, and instead of using LeafPad, I was just using Vim to write some files. And as I used Vim to write some files, it wrote to a whole load of blocks that it had never seen before that were all zero to start off with, and it wrote zeros to them. And I've no idea what in the file system handling Vim triggered to do that. But it was really strange. It just wrote zeros across a whole load of blocks which were already zeros, and it had never read from the file system. So I don't know if anyone knows anything about FAT16 file systems and wants to have a chat about that. I may be interested. So what we do here is we cache the blocks on the read. As the write comes through, we drop the write command. We let the data from the write command come through, and we update the cache, and we log this diff. And then we drop that write, and then we just return that fake OK message again. So again, the host thinks that it's being written, but it's not being written, and we're able to examine what's going on. You could, of course, not drop those. You could still cache them and not bother dropping the writes, but it didn't seem worthwhile for me. So, and this is the experimental part. I was having a discussion about this last night, and we had this idea that maybe you want to block some of the writes. You want to block, you plug the thing in, and you think, oh, if there's a device that's going to try, there's some malware that's going to try and write to it instantly, I want to block that. But later on in the day, I might just want to write something quickly. So it'd be really nice to turn the write blocking off and then turn it back on again. And reasonably, you could do this using a GPIO pin on the BeagleBone Black's headers, but I couldn't find a paperclip. So I wrote an in-band signaling system that is super hacky, and I wrote this at 6 o'clock this morning because I thought it would be fun to demo it. So this was not intended to be in my talk, and I'm really sorry if it fails, but we'll give it a go. So essentially, what we want to do is we don't want the host to know anything about this. We don't want the sketchy system that we've just plugged our USB stick to know that we've got a write blocker running or anything like that. So we can't present a special USB device. We've got to present as exactly as a USB mass storage device. So we can only interact with it as we would any other mass storage device. So what I decided to do was send the signals as if they were writes to the file system and have my code on the BeagleBone try and pick up where those, try and look at those data blocks and see if it could pick up the changes and use them as a kind of key to turn it off and on again. So I used file system writes. And this is called the in-band signaling mode. Okay. So, oh, just popped up on the wrong screen. So what I'm actually going to do is switch to this one. Kill that. So I'm going to write a file called A. So it's still blocking the writes at this point. I'm going to write a file called A. I am going to write a file called unblock. I'm going to write a file called B. And I'm going to write a file called reblock. And then I'm going to touch a file called C. All right. And we can see all those files are there because they're still cached in the file system controller and things like that. But if I eject the device and I pull it from here and I plug it into my host, what do you think is going to have happened? And the obvious answer is my demo didn't work properly. And I had not considered some aspects of how the file system works. Oh, that's slightly annoying. Open. So what I actually get, and I know what the problem is here, is I get A, B, reblock, and unblock. And the reason I get these is because I have no files on the device, which means they're all written to the first 512-byte block of the file system. So even though A was written and when we were still blocking, that write was blocked. And then we undid the write blocking, and then B was written. And at the point B was written, it rewrote that entire 512-byte block with A and B and unblock in it. And then reblock, because at that point we're not blocking writes, we let that one go through. That one's always going to go through. So what I realized is, yes, it does technically work because it still blocked C. And it did block A, I promise you. But then it rewrote the same block and just rewrote all the data. So if these were bigger files, this would have worked as a demo. And if I was smart enough to have checked the diff of the write and only write the diff for the new block rather than the diff for the original thing, that would have worked as well. But that would have meant I had to get into the internals of how the file system is storing those files, because the file system would get incredibly confused when it tried to write this block that says, I've got file A and file B, and you modify it to just say, no, you've just got file B, because file B will be in the wrong place for the file system. So it could feasibly work, but it's a really, really stupid thing to do. And actually, the smart thing to do is just to put a switch on the BeagleBone and use that. But I was running around my hotel room this morning looking for a paperclip to short 2 GPIO pins. I'd written code for it and everything. I was trying to short the pins, and I could not find one, so I decided to just waste an hour hacking this up instead. So that's pretty much coming to the end of my talk. We're working on a whole bunch of things still. USB 3 would be lovely, but obviously none of the cheap hardware. There's no $40 hardware that supports USB 3 man-in-the-middle stuff. So we're going to use Daisho, which is a project I've been working on for about a year with Mike Osman and a few other people, Mike Kershaw, Jared Boone, and a few people. I've had a sort of a first pass at writing a Python bindings. And Python bindings are super useful for the next thing we want, which is FaceDancer Compatibility. Because there's a whole load of code out there that works with the FaceDancer to do things like driver fuzzing and stuff like that. And it'd be really great to run them on here, because on this it could run at almost 480 megabits. It's not quite that fast, but it could run at much higher speed. But with the FaceDancer, it's a lot slower. There's a lot greater turnaround time. I'm sorry, Sergey. So this is a bit faster, and it will enable us to do like more interesting things. It also means you can not worry about having to poke registers in the Maxim integrated USB chip, which the FaceDancer code has to do at the moment, and things like that. So there's a slight different. Okay, not anymore, because no one needs a FaceDancer anymore, because they can get USBProxy. I mean, USBProxy is at a higher level than FaceDancer, so FaceDancer is still required for different things, but we kind of do very similar tasks but operate at slightly different levels. But hopefully we should have some code working soon that will go the same. Just want to say thanks to Adam Stasiak, who wrote a big bunch of it, Travis and Sergey for being very helpful and being very nice about the fact that I always say mean things about FaceDancer, and Mike Ostman for continuing to pay me even though I work on this the whole time. And any questions I don't have time for, but I will be outside right afterwards for anyone who's interested. And this is how you can get in contact with me or get the code for the project. On the GitHub page, there is an SD card image that you can just write to a micro SD and plug into the BeagleBone, and it will just start working, hopefully, ish. That's it.
Guys, if you have any questions, we have time for a couple of questions.
We
have a couple of
minutes.
Sorry,
I misjudged the time.
If you have any questions, put your hands up, and I'll come over with the mic.
Sorry, I should plug this back in then.
Don't be afraid. Put your hands up.
Any questions? Someone.
Great. Well, if there's no questions.
There you go.
No,
Two questions.
Hi. Yeah. Sorry if this is a very basic question, but what is like so good about the BeagleBone? I haven't really done much with it.
So there are a couple of things that I like about BeagleBone. And the reason the BeagleBone works for this is it has both a host and device port. So I just plug into either end of it, and it's nice and easy. It runs Linux, so I don't have to worry about writing firmware for it or anything like that. All my stuff is written in relatively kind of high-level code. It's like $40, so it's cheap. And it's open source hardware, which is the same thing as like all the other projects we work on are open source hardware. So that does mean something to some people and not to others, but that's kind of why we use the BeagleBone Black. Also, once I bought one, that was just the device I started using, so I haven't changed from that. But they're really difficult to get hold of at the moment. How does it compare to the Raspberry Pi? I'm not a huge fan of I don't dislike the Raspberry Pi. There's nothing wrong with it. But so, for example, for this project, you can't use a Raspberry Pi because you don't have a USB device side. So you can't act as a USB device as a Raspberry Pi. So that's.
Have you considered the applications of using the man in the middle, of modifying the data in some sort of exploit process in which like a signed image is verified first, and the verification process opens a file handler to verify the signature, and then secondly opens another file handler to actually read in the data?
So what you're saying is if host code has like a two-stage process, one where it reads the file, verifies it, and then actually reads the file for other purposes.
Right.
Could I fake the data the first time and then change it the second time? Yeah, but yeah, absolutely, you could do that. There's no reason you couldn't do that at all, and that would work. That would be pretty simple to write with this stuff. You'd need to know more about how the file system works. So at the moment, I was trying to ignore the file system as much as I could, but there's no reason that wouldn't work with this code. You just have to probably find some sort of library or write some code to handle whichever file system you're targeting. And obviously, it's not going to be file system agnostic, whereas this code reasonably should be if I could get any other file system working with it. Is that it? Any other questions? One more.
Did you mention what throughput that you have using the BeagleBone Black for reading and writing?
Yeah, I haven't tested it, and this is terrible because this is not the first talk I've given about USBProxy. And the previous talk, there was a question about what throughput do you get on it. And at the time, I was only using keyboards. And now I'm using mass storage devices, so I really should be able to experiment with what throughput I get. I don't know, but I can probably take my demo kit outside in a minute and just try to write a really big file to it and give you a rough estimate. So I'll be around and we'll try that. It's much higher than FaceDancer, but it's much lower than it would be if you directly connected it, I think. And it also depends on what I'm doing in the middle. So if I'm caching the pages, then I've got all the other screwing around with writing stuff to RAM on my device. But if I'm not, and I'm just passing the data through, then obviously it's much quicker. But it depends what you want to do with it in the middle. All right.
Great. Well, if you have any other questions, I'm sure Dominic will be around for a little while.
all day.
So hands together for Dominic.